Hello, this is third final part of lecture 6 of linear algebra, and this part is about conic sections. This topic will not be assessed, it will not appear on the test, but I think it's a nice topic to cover in this course because it's a very nice application of orthogonal diagonalization, as you will see soon. Okay, to start with, let me consider one very explicit example. And this example very soon will look familiar to you. And we consider a curve in the plane, which is given by this polynomial equation. This polynomial is of degree 2 in two variables, x, y, and it gives us some subset in R2. And if you remember a little bit earlier in this course, we called such curves conics. Yeah. However, right now, we don't know how the subset may look like. It actually can be empty set. We don't know. It's just some polynomial equation. We can hope that this is a nice curve. If we use some computer algebra package like Magma or Maple or MATLAB, or if you use a Python, you can actually plot this curve. And you can actually see that this is a curve, and you can see that this is an ellipse. But we want to do the same algebraically. We don't want to use computer algebra package right now. We want to apply some tools which we developed during the orthogonal diagonalization to actually plot this curve by ourselves without help of computer to see how this curve looks like. However, first we need to use one very nice, very important trick or observation, which is actually very powerful. And this trick is actually looks very simple, but it's not so simple. The trick is to rewrite this equation, this polynomial equation, into the following matrix form. Okay, convince yourself that this equation and this equation is the same thing. Okay, look what we did here. We have 5x squared, so you put 5 in this place, like first row, first column. 5y squared, you put 5 here in the second row, second column, yeah? And 6xy, you actually divide it by 2 and you put in these places, here and here. So the matrix is symmetric. Actually, if we wish, we can use non-symmetric matrix. We can, for example, put here any two numbers whose sum is -6, and we're still going to get the same equation. But the good thing that we can use symmetric matrices, yeah? So this matrix is symmetric, and this is crucial. This is basically the link to the previous topic, orthogonal diagonalization of symmetric matrices. Okay, this trick is powerful because it allows us to study nonlinear objects using linear algebra methods. Linear algebra study system of polynomial equations of degree 1. This is polynomial equation of degree 2. But still, we able to study it using methods of linear algebra and using basically the topic of orthogonal diagonalization. You will see how in a second. But I think this trick is very, very nice. Okay, so we already know that we're going to use orthogonal diagonalization at some point, but you may also remember that we made this matrix in the very end of the previous part of this lecture. We actually diagonalized it orthogonally, explicitly. We found a matrix P, orthogonal matrix P, such that P times this matrix times inverse of P is a diagonal matrix. Yeah. So and a little bit earlier in the first part of this lecture, we completely classified orthogonal matrices 2 by 2. And we know that these orthogonal matrices can be of two kinds, either with determinant 1, and then this is just rotation, or with determinant -1 when it's a reflection. But we didn't mention this in the last lecture. but when we orthogonally diagonalize 2 by 2 symmetric matrices, we can always choose this matrix P, orthogonal matrix P we're using, to be a matrix with determinant 1. Why? Because when we choose eigenvectors, we can always multiply one of them by -1. It's going to preserve orthonormality, but it's going to change sign of determinant. Yeah. So basically, in all examples in the previous part of this lecture, when we consider 2 by 2 matrices, our matrices P, which we use for diagonalization, these are just matrices of rotation. Okay. Anyway, we already know that we're going to rotate something. So let's rotate. So let's consider rotation of the plane around the origin and anti-clockwise. Yeah, let's call this rotation psi. And the rotation psi is basically a linear operator whose standard matrix is this. Yeah, we already discussed this many times. And these are all orthogonal matrices 2 by 2 whose determinant is 1. Yeah, in coordinates, this is our formula for the rotation. Yeah. Okay. Why do we want to rotate the plane? Because it may happen that if we rotate the plane, we of course also rotate the curve. Yeah, everything is rotated, and maybe the equation of the curve after rotation is going to be slightly simpler than this equation, and simpler and in such a way that it's actually easier to plot without any help of computer. Okay, so let's try to do this. So we fix rotation. We don't know the angle of rotation. We're going to choose it later. But let's first to see what's going to be the equation of the rotated curve. How to find the equation of the curve C after rotation. Okay. To do this, we introduce actually rotation into the around the origin by the same angle clockwise. Let's call it phi. Phi is an inverse linear transformation to the rotation psi. Yeah, if you rotate by angle theta anti-clockwise, or if you rotate clockwise, this is the inverse function. Yeah, and the fact that they're inverse, basically that the composition is identity. Psi composed with phi is identity. Phi composed with psi is identity. Yeah, good. So we apply our rotation psi, rotation clock counterwise around the origin. Yeah, and we just make this observation that point xy is contained in the rotated curve psi of c, if and only if point phi of xy contained in c. Yeah. Why? Because phi and psi are inverse to each other. So if you have this condition, just apply phi to the left-hand side and to the right-hand side. Use this equality, that the combination is identity, and you get this condition. So this condition and this condition, it's the same thing. Yeah, but this condition we can easily translate into equation. Why? Because look, what is phi of xy? It's just this point. So this condition means that this point is contained in the curve C. Okay, but how to check this condition? Straightforward. We know equation of curve C, so this point is contained in the curve C if and only if you substitute this point in the defining equation of the curve C, and you get new polynomial equation. This is what I did in here in this last line of the slide. It's a little bit small font. Font is a little bit too small, basically because in order to squeeze this long formula into one line on this page. Yeah. So basically, this is the equation of the rotated curve. If you if you rotate our plane by angle theta clock counterwise, then rotated curve C, psi of C, is given by this equation. Yeah, it's very, very explicit. Okay, so what we're going to do, we're going to basically simplify this equation, and you're going to have some term x squared times something, y squared times something, x times y times something, and then some constant term. And then our basically observation that it would be nice to find such theta such that the xy term disappear. If we only have x squared term, y squared term, and a constant term, this equation is actually quite easy to plot. This xy part make it a little bit more complicated to plot. So this is what we actually want to do. We want to simplify the defining equation of the curve C. But let us translate it into the matrix language. Yeah, this is a usual equation, but we want to use this trick which I described on the previous slide. We want to use matrix equation of our curves, which are given by polynomial equation of degree 2. Such curves we call conics. Yeah, okay, let's do this. So basically, the equation on the previous slide, which we found, is this equation. Indeed, we had equation before xy times this matrix times xy minus 4 equal to 0. What we did, we replaced the point xy by the point phi of xy. And phi of xy, it's exactly inverse of m times xy. But m is orthogonal matrix. So its inverse, it's transpose. So this is our point phi of xy. And when you take its transpose of this vector, transpose of the product of two matrices, it's a product of transposes of these matrices taken in the opposite direction. So if you take transpose of this vector, you get, of course, this vector. Okay, so this is our equation. So we had equation xy times this matrix times xy minus 4 equal to 0. Now we had almost the same equation, but instead of matrix 5 minus 3 minus 3, 5, you get this equation. Yeah, okay. And this basically show you how orthogonal diagonalization is related to this topic. Because look, M is orthogonal matrix. So its inverse is M transpose. M transpose is orthogonal matrix. Its inverse is M. So basically, this is what we did in the orthogonal diagonalization topic. We, during the second part of this lecture, we were looking for orthogonal matrix M such that this resulting matrix, is just diagonal. But if this matrix is diagonal, it exactly means that in the defining equation of our rotated curve, there are no xy term. Xy term actually comes from this part and from this part. If after multiplication by these two matrices, these two entries become 0, this is exactly what we want, but this is exactly means that this resulting matrix is diagonal. Okay, and actually we already diagonalized orthogonally this matrix in the previous part of this lecture. So we actually know the angle on which we should rotate, by which we should rotate. Yeah, this angle is actually minus pi over 4. Okay, namely, in the previous part of this lecture, we found this matrix, such that if you consider this product, this matrix, we call it P in the previous part, times this our matrix, and this is the inverse of P, or P transposed. Yeah, then what we get a diagonal matrix, 2, 8, 0, 0. Okay, good. So we know that how to find these matrices. Basically, in the language of the orthogonal diagonalization topic, this column was the eigenvector of this matrix, which correspond to the eigenvalue 2, and this column was eigenvector that correspond to the eigenvalue 8 of this matrix. Yeah, so we found this matrix in the previous part of this lecture. Yeah, and we already know this product is 2008. Okay, what does it mean geometrically? It means geometrically that our rotated curve psi of C is given by this equation. But this equation, this matrix equation, we can rewrite it back into the usual algebraic shape form like this. Yeah, this equation is actually relatively easy to plot. This is an ellipse, yeah? If you just scale x coordinate and y coordinate, you basically get equation of a circle. So this looks like a circle a little bit like extended, yeah. So okay, we call such curve ellipse. In some sense, you can use this approach to define what an ellipse. There is geometric definition of an ellipse, and there is algebraic definition of an ellipse. For example, using algebraic definition of an ellipse, you can define ellipse in this way. It's some curve such that after rotation and maybe translation, the curve looks something like this, maybe with different numbers. Okay, now let us give a definition. To be precise, let us give a definition of conics in the plane, which we already implicitly gave earlier, a few weeks ago. And we use this definition to basically start a game. We want to consider some curves in the plane, which we're going to call conics, and we're going to classify this curve, classify them up to rotations and also up to translation when we change the origin a little bit. Okay, to be precise, let's consider this definition. We say that a conic in the plane, or sometimes people call them conic sections. This is historical name because all these curves can be obtained by cutting a cone by a plane. But word conic, more modern, you can say just conic in a plane is a curve given by polynomial equation of degree 2. Here, a, b, c, d, e, f are some constants, some numbers, and we assume that a, b, c are not zero simultaneously. Why? Because if a, b, c all zero, this is polynomial equation of degree 1, and we know this is a line. This is not a conic here. So we want really this curve to be a conic. Okay, there's a small problem with this definition, namely that it may happen that these numbers a, b, c, d, e, f are chosen in such a way that this equation doesn't define anything that looks like a curve. Imagine you can have equation x squared plus y squared plus 1 equal to 0. This is one of these equations. But this is an empty set. Yeah, there's no point that satisfies this equation. Yeah, there's no point xy such that x squared plus y squared plus 1 is 0. Yeah. So basically, the small problem with this definition that sometimes this equation doesn't define us a curve. So when we give this definition, when we say the curve, we implicitly assumed that what we get is something that looks like a curve. Yeah. Okay. So if everything is fine, we're going to get 3 typical curves that can be given by this equation. One type we already met in the example which considered earlier. This is an ellipse, something that is given by this equation, 2x squared plus 8y squared minus 4 equal to 0. This is something like a circle. This is a very important type of curves. For example, you know that Earth rotating around Sun exactly by an ellipse. Okay, and there's another type of conics which are also extremely important for mathematics and physics and for many different other sciences. So it's called hyperbola. A typical equation is like x squared minus y squared equals 1. But I put all of them in this form. Yeah, x squared minus y squared minus 1 is 0. Yeah, such curve we say it's defined hyperbola. Again, there are several ways how you can define hyperbola. There are geometric way. There's algebraic way. We basically will define hyperbola a little bit later when we classify all such curves. Yeah, and this equation is defined parabola. This is the most typical equation. Basically, the first nice equation which you meet in calculus. Yeah, you consider the graph of function y equal x squared. This is parabola. Yeah. Okay, good. We called all such types are non-degenerate type. These are good conics. However, there are conics which are not so good. Some of them are bad, some of them are very bad. Let's consider them. So, for example, you can consider equation xy equals 0. If you think about this, when x times y is 0, it's even only if either x is 0 or y is 0. So this basically means that this equation defines a union of two lines. Yeah, if it's so you can consider union of two lines to be a conic, but of course it's not very nice conic. Yeah, it's what we can say it's reducible. Yeah, because it's corresponding polynomial xy. It's reducible polynomial. It's a product of two polynomials of smaller degree. Yeah. Okay. Anyway, this is still one of the subsets in the plane which is given by this equation of degree 2. Okay, our polynomial can degenerate even more. We can have equations like this: x squared minus 1 is 0. This is the union of two parallel lines, x equal 1, x equal minus 1. We can have even further degeneration. We can consider equation x squared equals 0. It's an interesting question. How should we consider this equation? Of course, this is just a line, x equals 0. But one can think of this as like a multiple line, like a line with multiplicity 2. Because if you consider this equation x squared equals 0 as a line, it basically means that you replace equation x squared equals 0 by equation x equals 0. Which is okay for geometrical reasons, but for algebraic reasons, this is not very okay, because you replace polynomial of degree 2 by polynomial of degree 1. You lose some information. Okay, anyway, geometrically, this is just a line. And we have further degeneration. We can, for example, consider equation x squared plus y squared is 0. And you may ask what it is. It's just a point. Geometrically, it's a point. But there's another way of looking at this equation. You can actually split this polynomial as a product x plus iy times x minus iy, where I is square root of minus 1. So over complex numbers, this is just a union of two complex conjugate lines, and complex conjugation change the points on these lines such that the only points which are real is the intersection points of these two lines, yeah, 0, 0. Okay, but over real numbers, this is just a point. And finally, we can have x squared plus y squared plus 1 equals 0. This is just an empty set over real numbers. Of course, over complex numbers, this is very nice curve, which is not much different from an ellipse. Yeah, you can think of this, that this is like complex ellipse. But of course, complex ellipse and complex hyperbola is the same. Very similar thing, yeah, because there's over complex numbers, all of them looks like ellipse, hyperbola, and curves like this looks more or less alike. We cannot plot them, of course, but algebraically they're very similar. Okay, anyway, these are all possible types of polynomial equations which you can think of. Of course, there are other polynomial equations which defines you the same subsets geometrically. For example, you can consider equation x squared plus 1 equals 0. This is, of course, also going to define you the empty set. But this empty set, algebraically, is going to be slightly different from this empty set. Of course, on the level of sets, this is the same thing. But if you talk about polynomials, if you just basically think about, okay, I just want to see how one polynomial differs from another polynomial, then x squared plus 1 equals 0, it more looks like this equation, yeah? And again, over complex numbers, it gives you the union of two parallel complex lines, yeah? And complex conjugation changes lines. Okay, good. So basically, we want to introduce some tools using the methods we described in the previous part of this lecture, such that I can apply this tool to this polynomial equation and immediately determine which type I have. For example, I don't want to plot this set, this curve, to see which type it is. I just want to be able to find this immediately using algebra and to determine immediately which type I am, ellipse, hyperbola, parabola, or maybe some degenerate type. And ideally, if it's degenerate type, it would be nice if I can say which degenerate type it is. If it's like a empty set, single point, single line, or maybe union of two parallel lines, or union of two lines. Okay, this is all possible. So let us consider basically the approach to this problem. Yeah. So approach to this problem is the same as we used in the previous example, in the first example which we considered. We just want to basically rotate the plane and simplify the defining equation of the curve. Yeah, so the idea is basically to remove this term. If you get rid of this xy term here, then if you just forget, for example, that this term is here, and someone asks you, hey, how to plot this curve, I guess some problems similar to this you probably already met in a school earlier. Or if not, don't worry about this. This is absolutely okay. We're going to do this now. But the idea that if you get rid of this term bxy, then you can group together x, polynomial in x and polynomial in y, and then you complete the square, simplify separately. X part of this equation, y part of this equation, basically similar to what you do when you solve quadratic equation. And then you simplify this equation even more by basically changing your x and y coordinate by translation. You, instead of x and y, you consider, you basically move all your plane by some vector. To every point you add some constant vector, which we usually call translation. Yeah. Okay, so basically we're allowed to use two types of transformations of the plane. One is rotation. Yeah, this is linear transformation. It's orthogonal transformation. Is given by this orthogonal matrix. Yeah, this is what we basically discussed already many times in this course. Yeah, but we also allow translations. If you look at the translation, you see this is unless alpha and beta in this example, unless zero, this is never a linear transformation. Linear transformation has to map zero vector to zero vector. Yeah, this function maps zero to zero vector only if alpha and beta are zero. Yeah, but still geometrically this is very nice transformation. You just shift all the points by the vector alpha beta. Yeah, so geometrically it's very transparent. Yeah. Okay, I may say that rotations are a little bit more complicated than translation. Yeah. So our goal to see how can we simplify this polynomial equation if we rotate and translate the plane. How can we simplify this defining equation of this subset if we just rotate our plane around the origin and translate by some fixed vector? Yeah. Okay, let's see the answer. Yeah, the answer is usually called classification of conics in the plane. Yeah, basically answer is like this, that if you have any subset in the plane given by polynomial equation of degree 2, then there exists rotation and translation such that the image of your subset after rotation and translation, it's one of the following types. Either this is an ellipse, which is given by this equation. Here, A, B are positive real numbers. Or it's a hyperbola, given by this equation. Here, A and B are positive real numbers. Or it's a parabola, basically equation is y equal ax squared. Yeah, okay. These are non-degenerate cases, and we may have degenerate cases. It may happen, as we already know from examples considered on the previous slide, that it may happen that after rotation our curve is a subset. Yeah, it's actually one of the following subsets: union of two lines, a single line, a single point, or an empty set. So on the level of sets, we should probably not consider any of these cases as a conic in the plane. Okay, maybe union of two lines we may consider as a conic, degenerate conic in the plane. But of course, if you have a single point or empty set, it's bad to call this set to be conic. So this is maybe a very bad case. This is bad case. This is also bad, I think. Line should be given by equation of degree 1, not by equation of degree 2. And union of two lines is not so bad. This can be considered like a limit case for example, for hyperbola. Yeah, if we take this equation, multiply 1 by some number lambda, and when you change lambda, your curve, its shape change a little bit. When you make lambda to be 0, your curve degenerates into union of two lines. So this is actually not so bad, but still we consider union of two lines as a degenerate conic. Yeah. Okay. There's another way how to look at this theorem. To be precise, what we're doing, we're not simplifying the subset. We actually simplifying the polynomial. Then we can be more precise. Behind any of this degenerate type, there is some polynomial. And sometimes these polynomials can be of different types. So for example, if you take an empty set, and if you ask yourself which equation of this type determine the empty set, you can name two. Yeah, one of them is x squared plus 1 equals 0. Another one is x squared plus y squared plus 1 equals 0. Or similar, you can multiply them by some positive number, negative number. Yeah. So, but these two equations are of different nature. Yeah, so one cannot be transformed into another using these types of rotation and translation. Yeah. Okay, so this is a more delicate questions which gonna follows from the proof of this theorem. This is the theorem. So let us prove the theorem, and the idea of the proof is absolutely the same as what we did in the first example. Yeah, in the beginning of this part. Okay, let's do this. So we fix the subset sigma in the plane. It's given by this equation. And basically what we're doing now, we want to simplify this polynomial in the left-hand side of this equation. We want to simplify this polynomial by changing variables. We allow orthogonal change of variables and also translation. We just change xy to x plus alpha, y plus alpha. This is translation and rotation. And we want to see how we can simplify this polynomial. Yeah. But of course, geometrical meaning of this, we want to see what happened with this subset when we rotate the plane or translate the plane. How its defined equation simplifies. Okay, first step, it's a main trick. You rewrite our quadratic equation into the matrix form. Yeah, this is a matrix form. In the example, in the first slide, we didn't have this part. Yeah, we only had this part and the constant term. But this is more general. You have quadratic part, part of degree 1, and then part of degree 0, constant term. Yeah. Okay, then the main, as we already know from the example in the beginning of this lecture, the main player here is this matrix. This matrix determines basically the type of your conic. Not completely, but if you know this matrix, you know almost everything about this curve. Yeah, and we know that okay, this is symmetric matrix, and we know that the main characters of this symmetric matrix, main features of this matrix are its eigenvalues and the corresponding eigenvectors. But of course, first we need to find eigenvalues. To find eigenvalues, we have to write down characteristic polynomial of this matrix. Okay, here is a characteristic polynomial. This is a lambda square minus trace of this matrix. Trace is the sum of diagonal entries, and then plus determinant of this matrix. Yeah, we already know that this quadratic polynomial has real roots. All its roots are real. This follows from the main theorem from the previous part of this lecture. Yeah, we called its roots lambda 1, lambda 2. And also notice that by assumption, we assume that A, B, C cannot be simultaneously 0. Yeah, otherwise this is just polynomial of degree 1. This basically means that this matrix N is not 0 matrix. This implies that at least one of these roots are not 0. If both roots are 0, this immediately gives us that this matrix is 0, which is not the case by assumption. Okay, good. So one of the eigenvalues is not 0. Since lambda 1 and lambda 2 are just names for them, we may assume that lambda 1 is not 0. Okay, lambda 1 is not 0. And we know that for every eigenvalue, we can find some eigenvector. So we find some eigenvector, v1, and and the proof of the orthogonal diagonalization theorem, we normalize this vector, eigenvector, in such a way that its length is 1. So we choose v1 to be eigenvector with eigenvalue lambda 1, such that alpha squared plus beta squared is 1. You just take any eigenvector and you just multiply it by 1 over its length. Yeah, and you get vector like this. Okay, then as we already mentioned in the previous part of this lecture, so if you have, you know that the second, we're able to find the second eigenvector for this matrix, which are orthogonal to this. Moreover, such that its two eigenvectors form an orthogonal orthonormal basis. Yeah. So, but if you have such vector alpha beta of length 1, it's actually very easy to guess the second vector which is orthogonal to it and which is also has length 1. You just have to swap alpha and beta and change sign of one of them. Yeah. So basically, if you denote alpha to be cosine theta and beta to be sine theta, which is possible to do because of this equality, then the second vector, second eigenvector of our matrix is just minus sine theta cosine theta. Again, we can multiply, of course, this vector by any number, and it's non-zero number, and it's going to be eigenvector. But we want two eigenvectors, which are first of all orthogonal, has length 1, and also we want them to be, if we want together these vectors to have form a matrix with determinant 1. So for example, if I multiply this vector by minus 1, our vector is still going to form an orthonormal basis of our plane. But we remember that later, like in the first example in this part of the lecture, we're going to form a matrix out of them. And this matrix, which we're going to use for orthogonal diagonalization. But for us, it's better if this matrix is a rotation. Yeah, because this is what we basically plan to do. We plan to rotate the plane such that the defined equation of our set, rotated set, sigma is simple. Yeah, so we want this matrix to be a rotation matrix. So if I multiply, for example, this vector by minus 1, I don't get a rotation matrix. I get a matrix of a reflection, which has a determinant minus 1, which I don't want. Okay, so good. So this gives me the orthonormal basis of R2, And if I put these two vectors together in the first and the second column of a matrix, I get a matrix of rotation. Yeah, okay. So I found the rotation, psi, yeah. This is a rotation by angle theta clock counterwise. Yeah, and as in the first example we considered in this part of the lecture, we denoted by psi its inverse rotation, inverse linear operator, which is basically a rotation by angle theta clockwise. Yeah, so theta is anti-clockwise rotation, and psi is a clockwise rotation. As I already mentioned, they are bijections. And point xy is contained in psi of sigma if and only if phi of xy contained in sigma. And absolutely like I did in the example in the beginning of this lecture, yeah, what to find the define an equation of the rotated set psi of sigma, what I should do, I should just take this point, yeah, and substitute in the defined equation of sigma. Yeah. Okay. So let's do this. Yeah. So I substitute, and this is my defining equation of the rotated curve psi of sigma. Okay. Look, I had equation xy times this matrix times xy plus de times xy plus f equal to 0. Now I replace everywhere vector xy by the vector xy times my matrix of rotation psi. So I replace it here. Before I had xy here, now I had xy times this matrix. Then I had xy here, now I have xy times this matrix. And this is just the transpose of this. Yeah, so this vector is just the transpose of this vector. Okay. And now I know from the theorem we proved in the previous part of this lecture, I know that I can find such matrix alpha, beta, minus beta, alpha. I can find such matrix in such a way that this matrix here between xy and xy, such that this matrix is diagonal. It's not just diagonal, it's a diagonal matrix with diagonal entries lambda 1, lambda 2. Okay. So if I know ABC, I know how to find this matrix alpha, beta, minus beta, alpha, and such that my equation becomes a little bit simpler. Yeah. So after I basically simplify this term and I simplify this term, my new equation gonna looks like this: lambda 1 x squared plus lambda 2 y squared plus this vector de times my matrix which I found, alpha minus beta, beta, alpha, this matrix of rotation, and times xy plus f. Yeah. Okay, it's very explicit. It's actually algorithmic. You can write a program that does everything for you here. Okay, and now we know what to do. Now, basically, we don't need, to be precise, from starting from this moment, you don't need matrices anymore. You can just play with this quadratic part of this polynomial equation in x separately, and separately with quadratic part which involves y. And then you simplify them. Okay, so we had equation that looks like this. We found a rotation psi by some angle such that our rotated set is given by equation that looks like this. So here d bar and e bar are new d and e. We had some before, we had d, e here, but after rotation they're going to change. And on the previous slide we explicitly put the formula how they're going to change. So we get some new numbers here, d bar and e bar, which is basically given by this formulas. Yeah. Okay. This equation is simpler than this. Why? Because it has one less term. Yeah. We don't have term xy here. Now is the goal is basically to get rid of this term and to get rid of this term. How to do this? By completing the square. You can take quadratic lambda 1 x squared plus d bar x and you try to complete this square. You can complete this square if lambda 1 is not 0. And remember, by assumption, lambda 1 is not 0. We mentioned that one of the eigenvalues, lambda 1 or lambda 2, is not 0. So without loss of generality, we assume that lambda 1 is not 0. However, lambda 2 can be 0. So we have this option. We definitely can complete this square, lambda 1 x squared plus d bar x. We take these two terms and we put them into, try to basically complete the square, like what we do when we solve quadratic equation in the one variable. But then, in what we should do, we should try to complete the square of the quadratic in y. But it may happen that lambda 2 is 0. And then in this case, we not able to do this. And then basically this term, but in some sense, this is not so bad situation, yeah, because if lambda 2 is 0, it means we don't have this term. It means our equation even simpler a little bit, yeah. And but then we cannot get rid of this part, yeah. Okay, so let's just do it, yeah. So we have three possibilities. We can have lambda 1 and lambda 2 can be both non-zero, and then the resulting equation going to be slightly different depending on the choice. Are they both positive or they of different signs? So we're going to consider two cases: lambda 1, lambda 2 positive, lambda 1, lambda 2 negative, yeah. And there is a case when lambda 2 is 0. But because I assume without loss of generality that lambda 1 is not 0, if you don't assume it, if you want to just write it down in most symmetric way, you just put lambda 1, lambda 2 is 0, the third case, yeah. So we deal with these three cases separately. So first we consider the case lambda 1, lambda 2 is positive, yeah. If lambda 2, lambda 1 is lambda 1, lambda 2 is positive, it means this two eigenvalues they have the same sign, either both negative, both positive. This but in particular they not 0, so we can make completion. We can complete the square in x and y simultaneously, and we basically rewrite our equation like this. Yeah. What I did here, I complete the square of quadratic in x, I complete the square of quadratic in y. This is what we do, how we find the formula for the determinant of quadratic equation, yeah. And this is what is left. Basically, this equation is the same equation as on the previous slide, I just rewrote it in this way. And now you see, if we consider translation, yeah, by this vector, okay, this is hard to pronounce, it's d bar over 2 lambda 1, e bar over 2 lambda 2. If you have this translation, that after translation, this term, the new equation of the translated curve, instead of this term, you're going to just have x squared. Instead of this term, you're going to have y squared, yeah? And this term going to be the same, yeah? So you get this equation. Okay, and again, this is some number which you can explicitly compute in every example. Lambda 1, lambda 2, your eigen values, you can find them. So now we have basically three possibilities. First possibility, if lambda 1 positive, lambda 2 positive, and this guy is negative, then this is an ellipse. Yeah, you can just plot it, and you can actually define ellipse to be the curve which is given by this equation with lambda 1 positive, lambda 2 positive, and this guy is negative. There's a similar case when lambda 1 is negative, lambda 2 is negative, and this number is positive. Of course, this is the same ellipse. You just can go from one to another by multiplying the equation by -1. Yeah, but there are some worse cases, some degenerate cases. You can have lambda 1 and lambda 2 both positive, but this number, for example, also positive. Then this is an empty set. There is no point that satisfies this equation. Everything is always positive. Yeah, cannot be 0. Likewise, lambda 1 can be negative, lambda 2 can be negative, and this number can be negative. Then it's also an empty set. And then we have a case when this number is 0. If this number is 0, then only one point that satisfies this equation is a point 0, 0. In all of these cases, these are degenerate cases. So, okay, so we can basically shortcut it, all these cases I described, by one condition. This is an ellipse. After rotation translation, we get an ellipse. The if and only if you basically take lambda 1 plus lambda 2, because we need to keep track of the sign. We know that they of the same sign, and multiply by this number, and you get, it should be negative. So basically the sign of lambda 1, lambda 2 should be different than the sign of this number. And this number cannot be 0. Yeah. Okay, otherwise we have some degenerations. Okay, this case is done. Lambda 1 times lambda 2 is positive. Let's consider the case when eigenvalues have different signs. Yeah. Then you actually can just repeat everything that I did on the previous slide, and you actually get absolutely the same equation. But now you have to keep in mind that lambda 1 and lambda 2 are of different signs. So one can be negative, but then another should be positive. Yeah. But then the only bad case here, if this number is 0, if this constant term is 0, then this equation splits as a product of two polynomial equations of degree 1. And this is nothing but the union of two lines, which we consider as a degenerate case. But if this number is non-zero, then this is always a hyperbola. Okay, always a hyperbola. Good, everything is done. And final case, when lambda 1 times lambda 2 is 0, but by our assumption, it basically means lambda 2 is 0, because without loss of generality, we assume that lambda 1 is not 0. Yeah. Okay, good. Let's consider the final case. Then we cannot complete the square because there's no quadratic in y. The y part of our polynomial equation has degree 1. So, but we still can complete the square of our quadratic in x, and we can simplify equation like this. And if you look at this, and if you say, okay, this is some number, yeah, this is some number, positive or negative, it doesn't matter. But what can happen that it may happen that, for example, this number e bar here, it is 0. If it is 0, then this is definitely a degenerate type. Yeah, it can be either union of two parallel lines, or it can be empty set. Yeah, or if this 0 and also this number is 0, this is just a line, equation of a line, but taken with multiplicity 2, because basically it's going to be just equation of a line squared. Yeah, but it's going to be like a vertical line. Yeah. So if conclusion, if this e bar is 0, it's a degenerate type. It cannot be something nice. Yeah. So we may assume e bar is not 0. But if e bar is not 0, then you can rewrite our equation like this. Yeah. Yeah, if e bar is not 0, you can rewrite like this, because you can divide by e bar. And then you can translate by this vector. Basically, you want this term to be new x and this term to be new y. So you translate your plane by this vector and resulting equation, the curve, the image of your curve after this translation, when we first rotate and then we translate, we apply this to every point of our subset, it's going to be given by this equation. But we know that this is parabola. Yeah, we can define the curve to be parabola. Yeah, to be precise, okay, this is, first of all, this is finish the proof of our theorem, of our classification of conics, but we can use this theorem, as I already mentioned, to define what are ellipse, what are hyperbola, what are parabola. Yeah, again, there are possibility to define them geometrically, which we're not going to do, because this is more algebraic course than geometric course. But algebraically, we can define what is ellipse, hyperbola, and parabola using our theorem. Yeah, we can say that ellipse in the plane is a subset such that it can be mapped by rotation and translations into a subset given by this equation. Yeah. For example, we could have here some constant term different from 1, but of course, if we multiply our equation by non-positive or non-zero number, we're going to get different equation, but the same curve. So up to scaling, we have these two parameters, A and B, yeah, and they have to be positive. This looks like ellipse. Quite often, your ellipse is written in slightly different equation. It looks like x over a squared plus y over b squared minus 1 equal to 0. This is another way, but it's a little bit more bulky. So I use this way. Okay. Likewise, we can say hyperbola is a subset in the plane such that if it can be mapped by rotation and translation to a curve that's given by this equation. Yeah, this is and again A, B are positive real numbers. And the same way we define parabola. Yeah, so this is a bit awkward, but in many books on linear algebra, including Pool book, parabola is defined as a curve that's given by the equation y equal ax squared plus bx plus c. Yeah, which is very weird because it basically means if you rotate parabola, say, by any angle, say by pi over 2, you don't get parabola in this definition. So this is, in some sense, almost coordinate-free definition. Yeah, it's any curve that up to rotation translation can be mapped to this curve. Yeah. So for example, if you have a curve x equal y squared, this is also parabola, of course. Yeah, it's enough just to rotate it by pi over 2, and you get equation of this type. Okay, good. So let us consider some examples. First, we want to use our classification theorem to be able to determine the type of a conic without plotting it. There are smarter ways of doing this, which we're going to consider a little bit later. But first, let us just illustrate our theorem, how we can apply our theorem. Okay, we consider this subset given by this equation, and looking at this equation, I have no idea what it is. It can be ellipse, hyperbola, parabola, maybe empty set. I don't know, maybe a point. But it's very likely that this is something nice. And of course, the title of the slide suggests that this is an ellipse. Let me explain how one can see this using our theorem and using basically the proof of our theorem. Yeah. So first step, we rewrite this equation in the matrix form. And then, of course, you compute the eigenvalues of this matrix. And okay, this is straightforward. You just write down characteristic polynomial of the symmetric matrix. You find its roots using the discriminant formula. And you get the roots are both positive. So since the roots are both positive, so the proof of our theorem tells me that if you remember how we proved our classification theorem, that after some rotation, my curve, okay, my set, the set sigma, is going to be given by this equation, where this is first eigenvalue, second eigenvalue, and D is some number. This number I can actually compute if I follow every step of my classification theorem. But I don't want to do this because it's actually very time consuming. So instead, let me just play some game. Look, I know that this subset after rotation is given by this equation. So again, if D is 0, this is just a point. If D is positive, it's an empty set. So if D is negative, this is an ellipse. So it's very small room for a choice, yeah? Empty set, point, ellipse. So for example, if I find 2 points on this curve, then it must be an ellipse. Yeah, that's it. This follows from the proof of our theorem. You can guess these 2 points. Yeah. So for example, you can just take, I don't know, take y to be 0. What happens if you take y to be 0? These terms disappear, these terms disappear. You have equation 5x squared plus 10x equals 0. Okay, it gives me 2 points, y0, x0. And the second point, y0, x is minus 2. Okay, good. So I just found, of course, this curve has a lot of points, infinitely points, but a priori I don't know this. So, but I just substitute y to be some number, and I try to use solve quadratic equation in x to find 2 possibilities for x. This gives me, in a good case, give me at least 2 points. So I just grabbed y to be 0, and I found x can be 0 or can be minus 2. So I get 2 points. So this cannot be empty set, yeah, because it already have 2 points. This cannot be a point since it has 2 points. So this is an ellipse. Okay, let's consider hyperbola example. We have this curve. We want to determine how it looks like, what its type. Is it like hyperbola, parabola, ellipse, or degenerate conic? So I first rewrite it in a matrix equation. Then I try to find eigenvalues. Eigenvalues are minus 3, 3, 2. So it's definitely not an ellipse, it's definitely not a parabola. So there's 2 choices. It's either hyperbola or something bad. But if you remember the proof of classification theorem, in the proof of classification theorem, we proved that after rotation and then translation, my equation of the curve of this subset gonna looks like this. First eigenvalue times x squared, second eigenvalue times y squared, plus some number, d. Okay, so if d is 0, this is the union of 2 intersecting lines. If d is not 0, this is hyperbola. Basically, these 2 options tells you that it's very unlikely that d is 0. Yeah, if you randomly take a curve like this, such that eigenvalues are different signs. And what does it mean, eigenvalues of different signs? It means basically the determinant of this matrix is negative. Yeah. What's the determinant of this matrix? Minus 2, minus 4, it's minus 6. So determinant of a matrix, of a 2 by 2 matrix, is a product of its eigenvalues. So we, in the case when eigenvalues are of different signs, so it's the same as determinant as negative. Yeah. So, but it's very, if I know the determinant is negative, it's very unlikely, it's possible, but unlikely that this number d after rotation translation is 0. Yeah. So how to check this? Okay, this is more tricky than in the previous case, but for example, you can take 1, 2, 3, 4, 5, you can take 5 points on this curve, or 6. So imagine if you, no, take 6 points, or maybe 5. If this curve is a union of 2 intersecting lines, that no matter which 5 points you take, 3 of them must be collinear, must be on the one line. So if you grab 5 points, are sporadic, some general points, some puts y something, find x, do it a couple times, you find 5 points, even you found 6 points. If you can find 5 points such that no 3 of them are contained in one line, which is not so complicated to check, then this is definitely hyperbola. Yeah, okay. In this example, I found 6 points. Yeah, very explicit. I just put x to be 0, then x to be 1, x to be minus 1. I found y, and I checked that no 3 of them are collinear, so this is a hyperbola. Of course, this is a very time-consuming way, because to check that no 3 of them of these points are collinear, this is time-consuming. So we will see a little bit later there's a simpler way how to determine that this is hyperbola. But first, let us consider the parabola example. Okay, I now take equation that looks like this. Again, I rewrite it as in a matrix form. We have the symmetric matrix. You check that the determinant of this matrix is 0, so it means one of eigenvalues must be 0. So in the proof of classification theorem, I assume that this 0 eigenvalue is lambda 2. Yeah. So this basically, the proof of my classification theorem in this case implies that up to translation and rotation, I have two options. Either my translated rotated subset is going to be given by this equation, so this is a parabola, or it's this y term accidentally disappear, and we get an equation that looks like this: 10x squared plus d equal to 0. D is some number. So if d is 0, this is just a line, okay, with multiplicity 2. Yeah, if d is negative, this is just a union of two parallel lines. And if d is positive, this is an empty set. Yeah, okay, so these are bad cases, these are good cases. Okay, we can argue as in the hyperbola case, but a little bit maybe simpler. If you grab, for example, if you find at least one point on this curve, then it definitely means this is not an empty set. If you find, for example, several points such that, like you find 3 points such that they're not collinear, they're not 3 points on this curve that not contained in the one line, this basically means d cannot be 0. You cannot have this case with d 0, because in this case it's line. Every 3 points on this curve must be collinear, contained in one line. And to distinguish with the case of two parallel lines, okay, if you manage to find 5 points such that, like with hyperbolic case, such that no 3 of them collinear, this is parabola. Yeah, I found these 5 points. You check, no 3 of them are collinear. How to check this? It's actually an interesting question. This can be done using linear algebra methods, and this implies that this is parabola. Oh, yeah. Okay. Of course, this was a very nice illustration of our classification theorem, but the last two cases, hyperbola and parabola, were a little bit time-consuming. Ellipse was okay, but hyperbola and parabola, time-consuming. So let us explain how one can do this a little bit in a better way, with some additional results. Okay, to determine the type of a conic, you actually do not need to consider to follow the proof of classification theorem. You can use a little bit more sophisticated approach. So first of all, you can rewrite the equation of my conic in this a little bit unusual way, but I must warn you, this is actually the best possible way by some reason which I don't want to describe now. So you introduce sort of like a dummy variable, like 1, and you rewrite this equation absolutely like we did earlier for 2 by 2 matrix, but now you rewrite it in like 3 by 3 matrix. Yeah. Okay, so sorry, I put here equation of a conic, explicit conic. This should be ax squared bxy plus cy squared plus dx plus ey plus f equal to 0, like in the very beginning. I will change it in the lecture slides after the lecture. Okay, so we have we rewrite it into this matrix form, yeah, and let's call this matrix M. And we denote by n our usual matrix, this A B over 2, B over 2, C. This is the matrix which we use in the proof of classification theorem. So we know that eigenvalues of matrix N, let's call it N, eigenvalues of matrix N, they determine the type of our conic almost uniquely. there are some discrepancies sometimes. Is it a bad case? So, for example, if the determinant of this matrix is positive, of n is positive, then it's very likely that this is an ellipse. Why? Because in this case, eigenvalues of the same sign, product of eigenvalues is determinant of this matrix n. So if eigenvalues are of the same sign, it's very likely this is an ellipse. Of course, it can be degenerate case, but if it's not degenerate case, it's an ellipse. Likewise, if determinant of this matrix n, if determinant of this matrix n is negative, it's very likely that this is hyperbola. Yeah, it can be, as we already mentioned, it can be something of degenerate type, but very unlikely. So it's very likely it's hyperbola. And if determinant of this matrix is 0, so it means one of eigenvalues is 0. If one of eigenvalues is 0, we know by assumption that second eigenvalue cannot be 0 because we assume the polynomial equation is of degree 2, not 1. So this is very likely to be parabola, but in some strange cases, it may be degenerate type. So basically, if we have some easy way to determine that our equation is not of the degenerate type, if we know that our conic is not degenerate, then it would be very easy to determine the type. So what is the condition that the conic is not degenerate? We need some condition that guarantees that our conic is either ellipse, hyperbola, and parabola. And this condition is very simple. The condition is the determinant of the 3 by 3 matrix is not 0. So if determinant of the 3 by 3 matrix is not 0, we know for sure that this is not degenerate type. Yeah. Okay. Almost like this. I'm thinking about, it's almost like this because I'm thinking in a complex world. In complex world, this is if and only if. In the real world, we have to be a little bit accurate. So first of all, if its determinant is 0, that it's definitely of a degenerate type, for sure. But if determinant is not 0, and for example, we in hyperbola case, if determinant of n is negative, then this is definitely hyperbola. Absolutely the same way, if determinant is not 0 and determinant of n is 0, we in parabola case, absolutely for sure. The only problem, the only case which this matrix cannot completely distinguish is ellipse or complex ellipse, like imaginary ellipse. Imagine that our equation looks like x squared plus y squared plus 1 equal to 0. Okay, what's going to be this matrix in this case? It's going to be just matrix 1, 1, 1. It's identity matrix. M is identity matrix. So its determinant is not 0, but it defines the empty set. But if you have a matrix 1, 1, minus 1, which correspond to the equation x squared plus y squared minus 1 equal to 0, then of course it's just a circle. So this is an ellipse, special case of ellipse, so it's not degenerate. So the only problem is with ellipse. So how to distinguish when it's ellipse or when it's imaginary ellipse? Again, if you have determinant of n is positive and determinant of m is not 0, there's only two possibilities. Either this is a ellipse, real nice ellipse, or it's something that given by x squared plus y squared plus 1 equal to 0, empty set. So for example, if you grab a point on this curve, if this point if your curve contains a point, if your subset contains a point, it's not an empty set. So in this case, this is definitely on ellipse. Or you can make it a little bit more wisely. You can actually, you have to check that, to be precise, that sign of your matrix or determinant of your matrix M and sign of your eigenvalues of n, they should be of different sign. So again, imagine x squared plus y squared plus 1 equals to 0. Okay, in this case, your matrix n is identity, eigenvalues 1, 1, and your matrix M is identity. So everything here is positive. Eigenvalues are positive, determinants are positive. So this is an empty set. This is not good. So this is controlled by this additional condition in this case. So if trace of matrix n times determinant of M is negative, it basically means that signs of eigenvalues of n and signs of sign of determinant of M are different. Yeah, then this is an ellipse, and determinant of n is positive. Okay, so the main slogan: if determinant of this 3 by 3 matrix is 0, this is degenerate case. If determinant is not 0, it's not degenerate, with one minor exception, when this can be imaginary ellipse. So if determinant of small matrix n is positive, and the sign of determinant of this big matrix M and the sign of eigenvalues, they are of different signs, this is an ellipse. If they are of the same sign, this is an imaginary ellipse, which is empty set in the real world. Okay, if you jump to complex world, then this two cases basically becomes the same. And the condition of the complex conic to be non-degenerate, it's very simple. It's just determinant of this matrix is not 0. Okay, but this is a complex world where life is a little bit simpler. Okay, let us show how to apply this result to determine the type of conic. Very similar to what we did before, but simpler, yeah, because we can use this nice condition. You take this equation, you rewrite it in the matrix form, but you compute the corresponding to 3 by 3 matrix M is going to be this matrix. This is going to be your 2 by 2 matrix, which coming from this quadratic part. Yeah, you check determinant of this matrix. Determinant of 2 by 2 matrix is positive. So this is either ellipse or degenerate type. But then you take determinant of M. Determinant of M is actually, in this case, it's going to be also positive. So since determinant of n is positive, it means eigenvalues of the same sign. How to see the sign of eigenvalues? Either both negative, both positive. But remember, the trace of a matrix, it's a sum of eigenvalues. Trace of a 2 by 2 matrix is a sum of its eigenvalues. So if trace is positive, it means both eigenvalues is positive. Okay, so again, how to kind of think about this condition? Imagine that after rotation translation, both your matrices are diagonal. So your matrix M going to be lambda 1, lambda 2, and some number. And your matrix N is going to be lambda 1, lambda 2. Okay, so how to distinguish the cases? So if determinant of M is positive and the eigenvalues of N are positive, this is your equation looks like lambda 1 x squared plus lambda 2 x squared plus some positive number equals to 0, which is empty set. Yeah. Of course, you can see that this is empty set by playing around with equation and wisely completing the square, something like this. Yeah, you can, for example, first take 2x squared and 3xy and try to complete the square of this guy. Yeah, and then you try maybe to complete the square of y, like wisely. Yeah, and you can rewrite your equation in this way, and you see this is positive, and this is positive. So you got an empty set. This is another way how you can actually determine the type if you just complete the square of your equation in such way. Okay, another example. using this 3 by 3 matrix M. Let's consider this subset. Again, this is an ellipse Y. We check determinant of 2 by 2 matrix is positive, determinant of 3 by 3 matrix negative, trace of your 2 by 2 matrix is positive. So you use a criterion which I described 2 slides ago, and you get that this is an ellipse. Again, if determinant of 2 by 2 matrix positive, it's very likely, highly likely means that this is an ellipse. But there is a possibility that this is an empty set, like imaginary ellipse. To get rid of this case, you have to use the trace of matrix N and compare it with the sign of matrix M. Okay, of course you can see this also algebraically. For example, what I did, I just play with this equation and I rewrote it in this way. Yeah, so basically this means if I change coordinate like this, yeah, then my conic can be given by this equation. But I must warn you that of course this is not orthogonal change of coordinates. This is a nice change of coordinates, like a linear change of coordinates plus translation, but it's not rotation composed with translation. So in the proof of our classification theorem, we only allow rotations and translations. This is rotations, translations, and also scaling. You scale x coordinate and y, and so it doesn't change the type of a conic, but it's of course change its shape. Yeah, so circle can be ellipse, but ellipse cannot become a hyperbola, and hyperbola cannot become a parabola. Okay, good. So absolutely the same way you can deal with a parabola example or hyperbola example. They are easier to determine if the given subset given by quadratic equation in the plane is hyperbola or parabola. You don't even need to care about the trace of matrix N. You only need to care about the determinant of N and determinant of M. If determinant of M is not 0, this is good, and it shows you that it's very likely non-degenerate. But if determinant of N is negative or 0 and determinant of M is not 0, then this is definitely not degenerate case. It's either hyperbola or parabola. Okay, good. So let me conclude this lecture. It was a little bit too long, but I hope it was enjoyable. This is more or less the final lecture for the linear algebra. The next week we're going to have a revision. There's going to be no new material, and the material of this part of this lecture, conics in the plane, it's not going to be examinable. This is just for fun. If you like geometry and if you like to apply algebraic methods to geometry, I think this is a nice topic. Okay, good. Let me stop the recording.